A malware sample that behaves perfectly in a lab environment and then turns hostile the moment it senses a debugger is not rare, nor is it accidental. It is deliberate engineering built around one goal: make analysis expensive, noisy, and unreliable. Welcome to BlueHat Cybersec Academy. And the uncomfortable reality is this: modern malware rarely tries to hide from systems. It tries to hide from humans studying systems. That subtle shift changes everything about how we think about security analysis. So if you're ready, let's walk through this properly, because we're going to break down how anti-debugging actually works in practice, why it exists, the main categories of techniques malware uses, and just as importantly, how defenders can think more critically about detecting and countering it. Not as a checklist of tricks, but as a logic problem shaped by adversarial thinking. Let's start with what anti-debugging really means at its core. It is basically a set of behavioral checks designed to determine whether a program is being observed. And if malware detects that it is under inspection, whether through a debugger, a sandbox, or an instrumentation tool, it may do a few things. It may terminate immediately. It may alter its behavior to appear harmless. It may delay malicious actions. Or it may even enter what looks like a decoy execution path. So the key idea here is important. The goal is not invisibility. It is misdirection under observation. And this matters because reverse engineering depends on a fragile assumption that execution inside a debugger reflects real-world execution. Anti-debugging techniques are designed specifically to break that assumption. Now, the first and most straightforward category is what we can think of as direct debugger detection. This is the obvious first line of defense from the malware's perspective. Here, malware may check for debugger flags hidden in process metadata. It may look for known debugger processes running on the system. It may even analyze parent-child process relationships that don't look natural. On the surface, none of this feels particularly sophisticated, but in practice, it works surprisingly often. And the real insight here is not about technical depth, it's about statistical expectation. Malware doesn't need to detect every possible debugger. It only needs to detect the most commonly used ones. That alone filters out a large portion of analysis environments. Then we move into something more subtle, which is timing attacks, when time itself becomes a lie detector. The idea here is simple. Debugging slows things down, so malware may measure the time between instructions. It may track execution latency of API calls. It may even rely on high-resolution performance counters. And if execution takes too long, it draws a conclusion. Someone is watching. Now, this creates a deeper problem for analysts because instrumentation always changes execution behavior. The more visibility you add, the more you distort what you are trying to observe. And even though modern tools try to minimize that distortion, timing attacks remain effective because they exploit physical constraints, not just software artifacts. Next comes exception and trap-based detection, which is a more interactive approach. Here, malware deliberately executes illegal instructions. It may trigger access violations on purpose. It may even use single-step traps, and then it watches what happens next very carefully. Because under normal execution, the operating system handles these events in one way. But under a debugger, those same events are intercepted, paused, and analyzed differently. So what the malware is really asking is simple. Did someone interfere with the normal flow of execution? And if the answer is yes, it immediately changes behavior. After that, we get into process environment inspection, which is where things become more introspective. At this stage, malware starts inspecting its own runtime environment. It may look for loaded modules associated with analysis tools. It may scan for memory regions that appear modified. It may check for unusual thread contexts. It may even detect suspicious API hooks. Now, this is interesting because it overlaps directly with legitimate debugging and profiling techniques, and that overlap is the real problem. The same visibility that helps defenders understand a system also creates fingerprints that malware can detect. So the tension becomes unavoidable. The more you instrument, the more detectable you become. Then we have virtual machine and sandbox evasion, which is one of the most widely used categories in real-world malware. Here, the malware tries to determine whether it is even running in a real environment. It may look for virtualized hardware indicators. It may check for low resource systems, like unusually small disk sizes or limited CPU cores. It may inspect generic or default device identifiers. It may also look for the absence of normal user behavior patterns. And the logic behind this is not technical, it's behavioral. Real users are messy. Real systems have noise. But sandboxes are often too clean, too consistent, too predictable. So modern analysis systems now try to fight this by simulating imperfection. Not just hiding virtualization, but adding delays, randomness, and human-like behavior patterns. Finally, we reach obfuscation through control flow manipulation, which is a different kind of strategy altogether. Here, malware doesn't even try to detect debugging. Instead, it makes analysis difficult, regardless of environment. It uses opaque predicates conditions that look complex, but always resolve in a predictable way. It applies control flow flattening. It inserts junk instructions. It even uses self-modifying code. And the goal here is not escape. It is cognitive overload. Even if execution works perfectly inside a debugger, understanding what actually matters becomes slow, confusing, and error-prone. So at this stage, the attacker is no longer fighting execution. It is fighting interpretation. Now stepping back, there is a defensive reality we need to be honest about. Anti-debugging is often misunderstood as something that blocks analysis completely. But in reality, it rarely does that. It mainly slows analysis down, distorts results, or forces analysts into indirect paths. So effective defense becomes a layered approach. You rely on multi-stage analysis environments that combine static and dynamic inspection. You use behavioral correlation instead of trusting single signals. You apply record and replay execution to reduce timing bias. You build instrumentation-aware tools that anticipate evasion patterns, and you compare across multiple malware samples to identify shared behaviors. The core principle behind all of this is redundancy. No single observation should ever be treated as final truth. And that brings us to the bigger insight, the part that often gets missed. Anti-debugging techniques reveal something deeper than technical tricks. They reveal a mindset shift in modern malware. Today's malware assumes it is being observed constantly, and it adapts to that assumption. So the real questions analysts have to keep asking are not just what the code does, but is this behavior genuine or conditional? Is the delay natural or intentionally induced? Is the environment shaping the malware more than the malware is revealing itself? Because that is where the real difficulty begins. At that point, malware analysis stops being just about reversing instructions. It becomes about questioning what the code is even willing to show you. And here's the closing thought to leave you with. Anti-debugging is often treated like a collection of tricks, but that framing misses the point entirely. It is better understood as a philosophy of resistance against observation designed specifically to exploit the very tools built for transparency. And that leads to a slightly uncomfortable truth. Visibility does not guarantee understanding. The real challenge is not simply seeing what malware does. It is recognizing when what you are seeing has been deliberately shaped to be incomplete. Before you go, let's turn this into something you can think about and respond to. If you were analyzing a suspicious binary and you notice this combination, execution slows down only when a debugger is attached. The program behaves normally in a virtual machine, but not on bare metal, and it terminates immediately when certain processes are detected. What would your first hypothesis be? And more importantly, which anti-debugging category do you think is doing most of the heavy lifting here? Drop your answer in the comments. And one more question to push your thinking further. If malware can successfully detect observation, what do you think is the weakest signal modern sandboxes still rely on today? And if this breakdown helped you understand how adversarial thinking shapes malware behavior, then you already know what to do next. Like, share, and subscribe, and explore more from the Malware Encyclopedia playlist, where we keep breaking down how real-world malware thinks, adapts, and avoids analysis in the first place.